We're given an electric field towards the left, a uniform field which has a magnitude of 100 volts per meter. And we're given 3 points, A, B, and C, and we're asked to figure out what is the potential difference VA minus VB and VB minus VC. So the whole idea behind this problem is we need to find a way to calculate potential differences from electric fields. Now in a previous video, we've seen what that connection is. We saw something, we realized that electric field is a negative potential gradient. Now, if you don't know what that means and you're not familiar with this connection, feel free to pause this video, go back and watch that video, revise the concepts and come back over here. All right, if you're cool with that, let's go ahead with this. Let's start solving the first one. What is the potential difference VA minus VB? How do we do that? Well, one way is we can use the formula, and we'll do that a little bit later, but I want to try and solve this logically. And for that, I asked myself, what does this number even mean? This number says that if you move along the field, then for every meter you go forward along the field, you will lose 100 volts of potential. That's what this number means. And if you're wondering, why do we lose potential as you go along the field? Well, if you keep a positive charge somewhere over here and let go of it, what happens? Well, it'll accelerate along the field, meaning it'll gain kinetic energy along the field, which means it'll lose potential energy along the field. Just like in the case of gravity, as things fall down, they lose potential energy along the field. So I know that if you go for every meter along the field, you lose 100 volts. Or every meter in the opposite direction of the field, you gain 100 volts, which means if there are 2 points which are 1 meter apart, I know that their potential difference will be 100 volts. So that means I just need to figure out how far apart these two are, and then I can calculate. So can you pause the video right now and see if you can, just using this information, figure out what is the potential difference between these 2 points? Give it a try. All right. So the first thing that comes to my mind is I just have to figure out what the distance between these 2 points are. If I know this distance, and let's say I find out that distance to be, and you can use coordinate geometry to figure that out, but let's say you get some number, if, for example, say 10 meter, okay, just an example. Then that means for every meter I gain 100 volts. So for 10 meters, I would gain 10 times 100, so 1000 volts. So would that be the answer? No. That will not be the answer. You can't do it this way. Can you pause the video and think about, okay, another thing, why you can't do it this way? All right. So this number that you gain or lose 100 volt per meter only works when you move in the direction of the electric field or in the opposite direction. Basically, you have to move parallel to the electric field. Only then you can say per meter you gain or lose 100 volts. So you can't move this way. So then how do I go from A to B? The way I like to do it is, one of the ways to do it is, you can go from A to B along the field first, and then you go up this way. I'll tell you why. See, when I go from here to here, I can use this number. I can figure out how far this distance is, and then I can use this number to figure out what the potential, how much potential I'm gaining because I'm going in the opposite direction. And now I'm going from here to here. Notice when I go this way, I'm moving perpendicular to the electric field. And we've already seen before that if you move perpendicular to the electric field, there'll be no change in potential. In fact, these 2 points lie on an equipotential surface. Remember, equipotential surfaces are always perpendicular to the electric field. So long story short, from here to here, there is no change in potential. Okay, so that means all I have to figure out is what is the potential at this point. I just need to figure out what is the potential difference between these 2 points. That's the same as the potential difference between these 2 points, because this and all the points lying on this plane would be at the same potential. Does that make sense? So I just need to figure out what this distance is. And I can do that by looking at the x coordinate. So this is -1. This is +4. So what is the difference between these 2 points? That's 4 minus -1, that is 4 plus 1. So that's 5 meters. And you can pause and you can just check that's right. So this is 5 meters. And so now I can use this number. I know for every meter I go forward, I gain 100 volts. So how much would I gain if I go 5 meters forward? I would gain 500 volts. So immediately I know that this point, which is the same as this point, potential-wise, is 500 volts more than this point. So let me write that mathematically. VB is 500 volts more than VA. And therefore, what I need is VA minus VB, so I can just rearrange this and I'll get VA minus VB as negative 500 volt. And we're done. There we go. That's the answer. Okay, now before we go forward to the next one, let's just convince ourselves we get the same answer by using the formula. This will be an excuse for us to get used to the formula. In a previous video, we also derived the formula. We saw that electric field, what is the connection between this and the potential difference? Electric field is the negative potential gradient, which means it's the negative difference in potential between 2 points divided by the distance between the 2 points. And again, this distance is only along the field, okay? So can you again pause the video and see, by substituting, you end up with the same answer. So give it a shot. All right, so if you rearrange, you get delta V equals minus E times delta R. Now, when you're talking about delta V and delta R, especially delta V, we need to be very careful about which is our initial point and which is our final point, right? Because when we're talking about change, initial and finals are important. Now, over here, we went from here to here, but you don't have to. You could have gone backwards as well. But just to keep things simple, I'll call this as my initial point and this as my final point. This point and this point are the same, by the way, like we just saw. Potential-wise, they're same. All right, so what is delta V now? Delta V is final potential minus the initial potential. So this would be VB minus VA. And that's why it's important. If you had called this as your initial point and this as your final point, you would call this VA minus VB. It'd be opposite. This equals negative. What is the value of electric field? Now we know the magnitude is 100, but what about the direction? It's in the opposite direction of the positive X. And that's important when you're substituting over here. So that means this is negative 100 volt per meter. So negative 100 volt per meter times, what is delta R? Delta R is you're going from here to here. So you're going in the positive direction. So that's plus 5. So 5 meter. So meter cancels and see what we end up with. We get 500 plus 500. So you get 500 volt. So VB minus VA is 500 volt, means VA minus VB is negative 500 volt. So you get the same answer. So you get the same answer. All right, can you think about what would be VB minus VC? Again, can you pause and try? All right, so because point B and C lie on the exact perpendicular, that is the equipotential surface, they are at the same potential, which means the potential difference between them must be 0. And so whether you take VB minus VC or VC minus VB, it should be 0. And again, I could ask, can we use the formula to arrive at this? Yes. This time delta R for them is 0. Because remember, delta R is the distance along the field. The distance along the field is 0. Are you getting that? Along the X direction, they have the same coordinate, and therefore delta R is 0. And then therefore you would get the same answer over here. All right, let's try one more. Okay, in this case, we are given an electric field pointing downwards with a magnitude of 30 volts per meter. We're given a point A whose coordinate is given to us, 3, 10, and there is a point B such that their potential difference is given to us this time. And so our goal is to find what the coordinate is. Again, can you try doing this yourself first? All right. So again, the first thing I want to try and do is see if I can do this logically. Now I know that the first thing I'm looking at is I'm trying to figure out whether B should be above A or B should be below A. It's given to me that VB is more than VA, right? It's a positive number. That means VB has a higher potential than VA. And so I'm just asking myself, if I go down along the field, potential will drop. Oh, so it has to be above. So B has to be somewhere over here. Somewhere over here. Okay, so that's the first thing I figure out. Now I know that for every meter I go up, I will gain 30 volt. But for us, I just have to gain 10 volt. So I ask myself, how many meters should I go up? I like to do it this way. I like to write it down. So I know for 1 meter, if I go up, I know I gain 30 volt. 30 volt. But it's given to me that I just have to gain 10 volts. So how many meters should I go? Well, it's 1/3, and therefore it should be 1/3 over here as well. So 1/3. So I divide this by 3, I get 10, right? So I divide this by 3, and so 1/3 meter, so that is 0.33 meter. So this distance should be, set that down, 0.33. So now comes the question, what is the coordinate of this point? So this point would be, well, the x coordinate would remain the same because x coordinate is not changing, so that's 3. The y coordinate would be now 10 plus 0.33, so it would be 10.33. And there'll be bar. I can put a bar over there. Now, one thing, just like we saw last time, this is not the only point that has 10 volt higher than point A. I can in fact have any point along this line perpendicular because all of these points on this line are equipotential. So point B can be here also. Point B can be this one. So point B can have any value of x coordinate because this is a uniform field, it can have any value of x coordinate, but its y coordinate has to be 10.33, which means the actual answer that we need to give if somebody asks us this question is we could say, hey, it can have any value. It's not that we don't know the value of x coordinate. We're saying it can have any x coordinate it wants. So I'm just gonna put x over there, pick any point you want, and y coordinate has to be 10.33. So this is our answer. And I encourage you to try and check this using the formula yourself.